requirements for being a professor. You have to be absent-minded, and you have to have a good enough voice to be able to fill an auditorium. So I try to work on both of those. Okay, so my name is Dennis Shasha, rhymes with cha-cha, the dance. Shasha. And I'm going to be talking to you about various puzzles today. Some of them come from this presentation, and some of them we're going to do things where you write down numbers, and I do mind reading and things like that. Okay, and I call them upstart puzzles because after the first few where we get going, there'll be puzzles where there are variants of those puzzles where I don't know the answer. And nobody, in fact, knows the answer as far as I know. So it's like an upstart, somebody who kind of gives you trouble, but it's kind of fun. And does anybody recognize those other two languages that are up there?
French.
French is which one? The casse-tête terrible. So terrible, you know how you say like, he's bad, and that's good, right? Well, terrible is like that. Terrible is kind of good. And what's the other one? German. German, yes. Artikel 18. Yeah. Yeah. Well, Nautisch means kind of like weird and uncomfortable making. So anyway. So why puzzles? Well, many of you already like puzzles, which is great, which I love. But the reason that I started writing puzzles for various books and stuff is that I believed in this heuristic. Heuristic being, if I have a difficult problem to solve, I try to make a puzzle out of it. And so one of the very first puzzles you'll see is one in which I was working for a company that was dominated the computer industry at that time. Shows you how old I am, which is IBM. Like completely dominant, like who ever heard of them now? But anyway, they existed. They still exist. Anyway, IBM completely dominated the computer industry to such an extent that the computer I was working on accounted for 1/4 of the gross national product when it came out. It was really a massive thing. And so they had this problem, which was how do you design circuits that can figure out whether there are errors in other circuits. And so, based on that, you'll see a puzzle. There are actually a few puzzles like that. Anyway, so Shockley, who's a co-inventor of the transistor, had always said that he tried to reduce problems to their kernel, and very often those kernels come out as a puzzle. So even if the problem seems complicated, you try to reduce it until what exactly is a difficult point. You try to solve that, and then you can maybe solve the rest of it. It works for me. So this is, I was telling you about my first job, and the first job was to find circuits that would fail intermittently. That means they didn't fail solidly. It's actually not so hard to find a failure if it's failed solidly. You know, if the circuit's always zero, then it's easy. The problem is when it's sometimes zero and sometimes it behaves correctly. And so an intermittent failure is like an intermittent liar. Somebody who doesn't lie all the time. Many of you have heard problems where people lie all the time. Those are actually much easier than when people lie only some of the time. So an intermittent circuit failure is like that. So let's look at that puzzle. So I call it the camper's puzzle. Now, if you're like me, well, hopefully you're not, you may have not liked your camp. I didn't like my camp very much. And so this reminded me of my camp counselor, who would lead us through the forest and get lost. But I'm imagining now life from the point of view of the camp counselor. And so the camp counselor is taking your scout group through the forest, and there are 8 scouts and the counselor. And now you're the counselor, and you're kind of reliable, except that you forgot which path to go down to find your campsite. So you're definitely going to be a professor one day because you're sufficiently absent-minded. So here are you, and you're coming on where the arrow is, and you're coming on that path, and you reach this intersection, and there are 4 paths leading from there. Okay, now, where this goes is that your campsite, darkness falls in an hour, your campsite is a 20-minute walk from where you are. So what you're going to to do is you're going to somehow split yourself up and your campers, well, not split yourself up exactly, but split up your group, including yourself, send them down, and send yourself down perhaps 20 minutes, have them come back, and then have them report on whether they found the campsite. That way there's 20 minutes down, 20 minutes back, that's 40, and 20 minutes to take everybody to the campsite. The trouble is that two of your campers sometimes, but not always, lie, but you don't know who they are. You just know that there are at most two of them. But because they don't always lie, you can't do something tricky like say, okay, are you wearing shorts today? And the person will either lie or not, and then you'll know that they're liars. They only sometimes lie. Now, it's very interesting to pose this question to people because whatever their profession is, especially adults, because whatever their profession is, they will use their profession. So even after giving all the same introduction I gave to you just now, I asked a psychiatrist and he said, you have to find those liars. But in fact, you may never find the liars. So, you don't have to find the liars. So, two of your campers sometimes but don't always lie, and the question is, how do you do it? How do you divide up your campers, and including yourself, so there are 9 people in total. How do you divide them up? You have 4 paths to explore, because you already came down one of them, you don't have to explore that one. 20 minutes down, 20 minutes back. Go ahead.
You put them by 3, so that let's say those 2 of the campers are in the same group.
Yeah.
There'll be one who's telling the truth.
Yeah.
But then you wouldn't know who's telling the truth. Which one? Okay, never mind.
Go ahead.
If this is cheating the question, then fine. But will the campers who sometimes lie always follow directions? So if you tell every camper, walk down the path for 20 minutes, then turn around and come back, is everybody guaranteed to do that?
Yes, everybody will do that.
Okay, so what you do is you say to all the campers, make sure that every path has at least one camper, and say, okay, go down. If you find the camp, stay there and don't come back. If you don't, after 20 minutes, turn around and come back. Then whichever path doesn't have the people that came back, that's the one you go to.
I see. Well, maybe they don't follow the directions to that extent. They'll all go down and come back. See, the thing is that the liars, they don't really care about whether you get to the campsite. They like brown bears. They like being mauled. Who knows? Yeah?
You have divided yourselves into groups of 3, then you pick 3 paths to go down. If you don't find the camp of any of those, then you go on to the other one.
Okay, so that was her suggestion, and she decided that wasn't good.
No, but you go down 3, then come back, and then if no one's found the camp, then because you would have at least one non-liar in each group no matter what, then you go down to the 4th path.
Okay, alright, so now suppose, so would you like to say why that doesn't work?
It doesn't work because in one group will have 2 answers, and you don't know which answer is the right one.
Right, so one group comes back and 2 of them say it's there, and one of them says it isn't, and everybody else says it's not. Then what happens? Who do you believe?
Then, if there's 2 groups with different answers...
No, just one group, that's it.
Oh, that means both liars are in that group, so it's...
No, you don't, because they may not lie, right?
Yeah.
I will tell you the answer before the end of the hour, but I'll just let it linger now for now. Okay. I won't tell you the answer, but I will tell you one little hint, though, actually. I'll tell you that you can explore one path all by yourself, because after all, you do trust yourself. Okay, it's not like some metaphysical thing where you don't trust yourself. Okay, so that might be helpful. Yes.
I just realized that there's another reason these send 3 campers down each path strategy won't work. You've only got 8 campers, so you need 9 campers to send.
But you have yourself.
No, there's 4 paths.
Yeah.
You go down one of them, you need 9 campers to explore the other 3.
Yeah.
You don't have 9 campers.
Right, but it turns out that you can do it with 8. Anyway, but you don't need to take any campers with you. That would be a little bit. And you may never discover who the liars are, in spite of what the psychiatrist friends thought. Anyway, one of the variants of this problem, which actually I do know how to solve, is could you do the problem with fewer than 8 campers? And there's actually a way to show that you can't. So, in computer science, very often you want to show that you can do something with a certain resources, but you can't do it with fewer. And this is a case where we can do that. Well, do you find it too frustrating? Should I
No,
give
you
you
have the answer.
Oh, you have an answer. Tell me.
If you don't explore one path,
Yeah.
and you go down one and you divide the campers into 2 groups of 4 each,
Yeah.
and they explore each one of 2 paths left. And then if 2 liars are in the same group, it'll be split 2 and 2.
Yeah. And then what do you do?
And then, I don't know.
So then you have yourself. You say no. 4 of them say no. The other 4 come back split. Who do you believe? They all look, they look as innocent and beautiful as you do. But you can't solve the problem without anything too tricky. But you're close. Okay. I will come back to it. I promise I will solve this for you. So, for me, puzzles are a way to make a living. In fact, I used to write the puzzle column for Scientific American, and I wrote down a few times, they said, so give us like a line about yourself, the magazine said. So I said, okay, write down that I create and solve puzzles for a living. And then one very angry reader wrote in and said, surely Professor Shasha does something else besides creating and solving puzzles for a living. Now, I didn't want to argue with the reader, because you don't argue with readers, but the fact is, that is what I do, is I create and solve puzzles for a living. So mostly try to solve them, but very often it's kind of like, how do you look at a problem in such a way that it's a puzzle? So for example, when I work with colleagues in biology, one of the problems that they have is that there are many possible ways of designing experiments, and they don't want to have to try all of them. And so the question is, can you try a good subsample? And so that's kind of a puzzle of sorts. And so I've used puzzle kind of solving techniques for that. And the way I put my kids through college, your parents are probably thinking about that for you too, right? Is I make people's databases run faster. And sometimes I don't even know what the database system is. Sometimes it's homegrown. Sometimes you can just kind of like sit down and ask the person, what is it that they're trying to do? And just see that they're really not doing it right. So very often there are puzzle solving problems like that. And then of course we're near Wall Street, and so there's a lot of finance stuff, and the next puzzle is inspired by that. So very often in finance, what you're trying to do is you're trying to get a small edge. It's very seldom that you can guarantee that you're going to win, but very often you can somehow, maybe by observing patterns and doing massive data analysis, you can say, if this happens, then that will happen. And so, it's hard to make that into a puzzle, so I'm somewhat abstracting it to this. Okay, so you're placing even money bets on the flip of a coin. And you may bet only as much as you have, so it's table stakes. And the whole game is 3 flips. Now, there is an oracle that knows the future. And it will tell you how the flip will go at least 2 of the 3 times. But it might lie the other time. Okay, so it's a little, believe me, not all of the puzzles are lying puzzles, but just those first 2. So don't think there's a pattern. But anyway, and the idea here is that you don't really know how some stock is going to go, but very often you're going to be right. Let's say more than 50%. So we have at least 2 or 3 of the 3 times the oracle will tell you the truth. The oracle doesn't like you though. So if you put down all your money the first time, the oracle will be sure to lie that time. Okay? Or anyway, the oracle will make it, let's say the oracle is so good, the oracle can read your mind. So if you bet heads, it will make sure that the coin comes out tails. Okay, the oracle can do that. But 2 out of the 3 times it has to tell the truth. And so the question is, if you start with $100, how much can you guarantee to have at the end of the 3 rounds? That's the problem I'd like to pose to you. And this problem I'm going to work through with you. And we'll see whether, because it's such a nice technique that we can use. And let's see what we get. But do you have an idea, first of all?
Okay, this might seem slightly too ambitious, but 99.98.
99, you start with $100.
$99.98.
No, but I mean, look, the oracle's got to tell you the truth 2 out of 3 times. Don't you think you can do better? Or are you saying that's your profit?
Well, I mean, I don't know the payouts here.
It's an even money bets. So if you put down $50 and you win, you receive an extra $50.
Ah.
But I like the precision of your answer. Happens not to be right, but I like the precision. Yes.
Well, I can immediately think that the first thing to think of is splitting your money evenly into 3 piles. So if you bet $33.33 each time, you're guaranteed to win 2 of them and you'll lose the 3rd, leaving you with a net total of $133.33.
Okay, that's nice. Okay, that's good. So now we have
I expect that you can do better than that. That's the first thing I thought.
All right, okay, so that's fair enough. But I mean, think about how you might be able to do better. Because like as soon as the oracle lies, then after that you can bet the farm. You know the expression bet the farm? You can bet everything you've got. And so as soon as you get 1 lie, you can do lots of cool things. And now if the cameraman would turn over here, I want to adjust. Okay, so what I propose to do is I propose to use what's called a decision tree, which you may have already seen in your life. But if not, I'm going to introduce it. It's a very easy idea. And we're going to use the decision tree to solve this problem. Okay. So, and what we're going to do is we're going to stay agnostic with respect to how much we're going to bet. We're not going to know that initially. We're going to figure it out using algebra later. Very elementary algebra. Algebra that I'm sure you all know. Okay, so the very first time, we're going to bet X dollars. We don't know what X is yet. Okay, so now either the oracle lies or it tells the truth. Meaning, because we asked the oracle at the beginning, what is it going to be? Oracle says heads, let's say, so we bet X dollars on heads. Okay. So now, if the oracle lies, we have 100 minus X here, because we've lost X. Because we tell the oracle how much we're going to bet. We've lost X. Okay, but now what can we do? Bet the farm. I want you to get into the expression. It's such a cool expression. Okay, you bet everything. Okay, now what will happen when we bet everything? Well, the oracle has to tell us the truth. So what happens after the next one, next round? How much do we have? Sorry. 200 minus 2x. And after the round after that? 400 minus 4x. Yeah, we all see that? Because each time we double. All right, now, suppose that the oracle tells us the truth. So now we have 100 plus x. Plus x. Okay, now, we don't know what to do. So we're going to bet y. And again, the oracle can either lie or tell the truth. Well, if the oracle lies, we have 100 plus x minus y, right? Should we all agree about that? Because we just lost y. And now what do we do? Tell us. What do we do now? Because the oracle lied. Bet everything. I can't get you to say bet the farm. Okay, fine. 200 plus 2x minus 2y. That's fine. Okay? Now, in this case, how much do we have? 100 plus x plus y, right? Am I losing anybody? Sorry. Okay? Yeah, because we won y here and we won x there, so now we have 100 plus x plus y. And now what do we bet? Nothing. Exactly, nothing. Okay, now, because we're betting nothing, what do we think about all of these guys on the bottom here? These amounts here. What constraint could we put on all of them? Do you think? I mean, let me put it to you this way. Suppose that this number were vastly more than this number, or even a little bit more than this number. Well, the oracle can always choose which way we're going to go. Because the oracle can read our mind too. So the oracle, in that case, if this number were greater than this number, the oracle would force us down this path. And if this were the worst, the oracle would force us down that path. So as a result of that, just by symmetry, and by the way, the inspiration for this is that what we're trying to do is we're trying to guarantee a result. So when I say the oracle can read our mind, really all I'm saying is that we're trying to guarantee something, so we have to assume the worst case. Now, okay, so now I'm not going to, I'm trying to make this not complicated, but so what we're saying basically is that all of these have to be equal. But that has to be equal to 400 minus 4x, and this also has to be equal to 400 minus 4x. And because they're both equal to that, they're equal to one another. Okay, now this is just algebra, right? You know how to solve these things. Would anybody like to take out a piece of paper and tell me what x and y are? Just for fun?
So it's 100 plus x plus y equals 200 plus 6x minus 2y, and then you just do it from there.
So you're saying from this we can conclude 100 plus x plus y is equal to what?
200 plus 6x minus 2y.
Why?
Plus 6x minus 2y?
Well, so, oh wait, 100 plus 5x plus y. Oh, no, wait, never mind. Not used it.
So what do we do in a situation like this?
I was isolating 400, so, because I didn't see that the 400 plus 4x equals 400 plus 4x. Never mind.
All right, so what would we do in a situation like this? Well, we can at least solve x in terms of y using one of them, and then substitute and put them in. Yeah, something like that. So let's take this first one, and so we have plus 5x plus y equals 400. And all I did was add the 4x to both sides. And then we say, okay, therefore, let's say y is equal to 300 minus 5x. Do we agree with that? All I did here was I subtracted 100 plus 5x from both sides. Okay. Anything mysterious about this? Okay, so now that given that, we can put that in here for the y. Yeah? Is this too much? Not fun enough?
-100
Okay, so we have 200 plus 2x minus 600 plus 10x. Yeah, why? Because this is 2y. That's 1y, so that's 300 minus 5x, but it's negative, so it's 600 plus 10x. Yeah, okay. Is equal to 400 minus 4x. Okay, it could be that I'm making a mistake, but I think it's okay. So here we have 12x and minus 4x. So what do we do? Would anybody like to give me an idea?
Negative 400
So this is negative 400 on this side, plus 12x is equal to 400
minus 4x.
minus 4x. Yeah. So we get 16x is equal to 800. So we get x is equal to 50.
Okay.
Yeah? So make any mistakes? Sometimes it's easier to see these things from a distance. I think it's okay though, yeah? So if x is equal to 50, then y is equal to what? Well, 300 minus 5 times 50 is also 50. So x and y are 50. Okay, so let's just check this. X and y are both 50, and what do we get from here? From here we get 400 minus 4 times 50, which is 200. From here we get 200 plus 2 times 50 minus 2 times 50, and also get 200. And here we get 100 plus 50 plus 50, we also get 200. So, we can guarantee to get 200. And, now suppose that somebody said, oh, but wait, maybe if I make x bigger, that'll be better. And you see, if you make x bigger, then what happens? The oracle goes, oh, you made x bigger, you fool. You made x, let's say, 75. So the oracle will make you lose the first time, and then all you have is you have 25 here, then 100, then 50, then 100. Okay, so you don't want to make x bigger. Now you say, well, maybe I want to make x smaller. Well, then the oracle will tell you the truth the first time, and then you can't get to 200 this way. Similarly with y. Make sense to you? Anybody need some candy to keep going? Yeah? Cameraman. Let us go back to the sentences. What would you like? What would you like? Caramel. Nice catch. Anybody else? Same? Caramels are good.
Caramel. Thank you.
Caramel? Or one of each? Two of each?
Caramel, please.
Caramel.
Thank you.
Oh, good catch. Anybody else? What would you like?
Caramel, please.
Oh. Good catch. Okay. Anybody else? Would you like something? What would you like? Which one? Milk chocolate? Caramel. We were running caramels today. Good. We've got time. Ah! Anybody else? Would you like something? Okay. So, that's decision trees. Decision trees turn out to be very useful. In fact, sometimes what I do when I'm working with biologists is that I construct a decision tree for them based on their data. So I might say, well, if you do this to this plant and that to that plant, and you combine those, then you'll get the result you want. And they're very happy because they understand decision trees, right? They're pretty easy. At each moment, you're just asking what's going to happen. Okay. Do you have a question, anybody? Okay, now,
Question?
yes.
It said, the slide just before this one said, this puzzle is easy, but wait until...
Yeah, well, wait until this.
Ah.
So, because I invent puzzles, I kind of get intimate with them. You know, we kind of become friends. But sometimes, those friendly puzzles that I invent to illustrate a principle kind of turn their back on me and they decide they're going to be much more difficult than I thought. So I'm going to now present to you some puzzles where, in fact, the right answer, whatever it is actually unknown. So, we're going to start with the amazing sand counter puzzle. So in cryptography, which you may have already taken some cryptography, I noticed that my student George Wong taught some. Did anybody take his class? Was he good?
Yeah.
Yeah, he's awesome. He took my freshman class and he's been doing research with me ever since. He's just a fantastic guy. All right, so a zero knowledge proof, did you discuss those? So zero knowledge proof, for the rest of you, is a proof where I convince you that I know something, but I don't tell you what I know. Okay, which kind of seems bizarre. Because usually in high school, if you say, hey, professor, you know, I really do know this, but you know, I'm not going to show you, you usually get an F for that. That's not usually good. But you see, in cryptography, this is a good thing. If you can prove that you know something, then people will say, aha, that person, you know, has signed this document, because only that person can do it. So it's used a lot for signature schemes. But we're going to abstract away from that to make it a fun puzzle. And so you're going to show that a prover wants to demonstrate that he or she knows something. It's going to be probabilistic, but it's going to be with such an overwhelming probability that we can be convinced. In fact, every time you buy something on the web, it's based on this sort of thing. It's all probabilistic. Now, of course, we see a lot of this, people, you know, claiming that they know stuff, like, for example, that they know God or something like that. And so it's not that kind of thing, but hopefully. So there are serious applications in cryptography, and we will discuss some of those, but before we get to those, we're going to talk about one of the most productive puzzles that was ever invented, which is called the spy versus spy problem. And then we'll get to the amazing sand counter. The spy versus spy problem goes like this, as you can see in the bold. So I'm going to let you read that for a moment, okay? So you have spies, you want to send them to the other side, but you know, when they come back, if they don't have the right signal, they might get shot. So you send them this way, the bold, and they come back that way, and you don't want the guards to shoot them, but on the other hand, you don't want the guards to let in anybody because those could be spies from the other side. Okay? And this is all fine. If you trusted everybody, this would be great. But the problem is that you want to have some kind of password mechanism. And the assumption is that the spies are, you know, high caliber people. They come to cSplash, they do cool things like that. But the guards, not so much. The guards, you know, they get drunk. You know, they dissipated lives. They could be bribed. All kinds of bad things could happen to the guards. So the guards will do their jobs, but anything you tell them that you consider to be a secret, they might reveal to the other side. Okay? So whatever you tell them will be known to the enemy, basically. You have to make that assumption. I mean, of course, there are going to be some good guards, but you're just going to assume they're all going to be leaky. So you have to devise a scheme where the spy will be able to safely come through, but the enemy will not be able to introduce its spies, and yet the guards, even if they reveal all their information, are okay. Now, on the face of it, this looks very difficult. Because if I say, let's say the password is abracadabra, well, if I reveal that to the guard, and the guard leaks it in the bar, then some enemy spy could come in and say abracadabra, and then the enemy spy comes through. So that would not be a good solution. Yes?
Could you teach the guard to recognize their faces?
Okay, that's a good question. You're very good at finding good questions that are outside the box. It's very good. I'd like to throw you chocolate for that.
Thank you.
So, yes, except that's why I showed you the spy going in one way, and then the spy coming out the other way. There are just too many spies. So we want to do it mathematically. We want to do it in such a way that the guard knows something, but even if they reveal that, it's okay. Now, the way that so you want to give some information to the guard, and you want to make it so that the guard can reveal the information without that causing any problem. So in the abracadabra example, that wouldn't be the case. So, the person who solved this is named Michael Rabin, and the person who posed it is a guy named John McCarthy. And McCarthy liked to pose puzzles, and Rabin solved it in the following way. So what he did was he said, well, a mathematician named von Neumann had the following idea to generate what are called pseudo-random numbers. You take an n-digit number, you square it, and take the middle digits, and that becomes the next number. So I'm going to just give you an example of that, and then we'll come back here. Well, in fact, here, let's write down the example on the board. I don't think they have it. So let's say that I start with a number. I might need help with the calculator here. I start with the number 341. That's my first number. Okay, could somebody square that for me, please? We're going to get the square of that number. And how many digits is that square going to have? Something like 6. Yeah? Go ahead.
I think it's 11628.
1, 1,
62.
6, 2, 6, 2, 8, 1.
Yeah.
Okay, good. So that is 6 digits, yeah? Now, we're going to take again, we're going to take the middle digits. Well, here it's not quite clear what the middle is, but let's say we'll take those middle digits. And that's going to be our next number. And then, in the case of the random number generator, we're going to take this number and we're going to square it. Somebody tell me what that would be? So this is the square.
26,244.
This is the middle.
244.
244. Okay, and then the next middle digits will... Oh yeah, oh, okay. Those will be the next middle digits. Okay, so now, as a random number generator, this is kind of nice because you can prove properties about this like that the numbers will be uniformly distributed in some way. But that's not what Rabin was using them for. So now I want to ask you, given this kind of idea, where you take a number, you square it, you take the middle digits, something like that, what information would you give to the guard, and what information would you give to the spy? And then what happens when the spy appears before the guard?
You tell the guard what the middle digits would be, and you tell the spy the number. So since it's very difficult to go against the arrows in the picture that you drew, even if the enemy knows, okay, the middle digits are going to be 624, it would be very difficult for them to figure out that the number the spy knows is 162.
Exactly. So let me just repeat that. He says you give the guard this. You give the spy that. The spy appears, and the spy says 162. The guard squares that, takes the middle digits, and says, 624. Cool, you're in. But now the guard has already gone to the bars and said 624. That's a great number. But now you'd have the problem of trying to figure out which number would have generated that by the squaring and middle digits business. Now, of course, if it's just 3 digits, you could try all possibilities. So you couldn't do that. But suppose it's 20 digits or 100 digits. Okay, that's a lot for the spy to remember. The spy might have just gotten shot at. Might be too much. But let's say that it was like 20 digits. That's something to remember. People can remember that. And the spies are like cSplash quality people, so they're really good. And so, they could do that. And even though the guard, may not be super reliable, the guard can use a calculator. It's okay. All right. And so yes, you get another candy for that if you like. What would you like?
The
plain
plain,
one?
yes.
So does that make sense? Okay. So now, here the guard is basically convinced that the spy knows something because the spy has been able to produce that. That's not quite a zero knowledge proof, because now the guard does gain some knowledge. It doesn't do him any good because that number is only used for that one spy. However, let's now look at the zero knowledge case. So here we have what I'm going to call the amazing sand counter. Okay, you can see that the amazing sand counter looks like a magician. Has a nice mustache and everything, and a good Dolly style mustache. I am the amazing sand counter. If you put the sand in this bucket, I know at a glance how many grains there are, but I won't tell you. Okay, which is a pretty impressive feat. And your problem is to design a protocol whereby you can test that the amazing sand counter can do what he says it can do. Okay, so here's the situation. Here's some sand. The amazing sand counter says, I know how many grains there are. And the question is, can you invent a protocol so that you'll either believe the amazing sand counter or not, but he's not going to tell you how many grains there are. Yes?
Tell him to square the number and then give him the middle square.
Okay, but how are you going to verify that?
Well, you put a specific number of grains of sand into the bucket, and then you perform the same procedure yourself.
Okay, you could do that. If you're willing to count on grains of sand, you could do that. But let's say you're not. Because, counting on grains of sand is kind of really tedious. That's really, really, really tedious.
Well, if the grains of sand are pretty homogeneous, you could just weigh the sand and then do a few calculations to figure out how much sand there is.
Yeah, if they're very homogeneous, you could do that. It's okay. Fair enough. It's definitely worth a piece of candy. It's not quite the approach that I'd like, but that's okay. Which kind of candy would you like?
Regular.
Regular. I'm going to do a better throw. The last time I gave you
I have a
that.
question.
Yes. Okay. We hope you don't get injured. Get to the candy.
Are you able to make another bucket of sand and know that there's the same amount of sand in those buckets?
What do you think? You're just a normal person, right? How would you be able to do that? You're not an oracle. All right, so let's just say this. Okay, so the amazing sand counter is amazing. He can look at a bucket and know these things, or at least claim that he knows these things. You're going to try to put him to the test, but he's not going to tell you how many grains there are. do? Well, I'll give you a hint. You can send him out of the room. You can ask Amazing, we'll call him Amazing for short, because Amazing Sand Counter is too much to say. You ask him to leave the room, you count a small number of grains, not the whole bucket, a small number of grains, like something under 20. You remove those, and then you say, hey, Amazing, come back. How many did I remove? Or how many did I add? Okay, and you do this 100 times. Okay, now either Amazing is so lucky that you want to go to Las Vegas with him, or he somehow can do this. But notice that you have never found out how many grains there are on the bucket. So, this is how these probabilistic proofs go. You don't actually know what he knows, but you know that he knows how to do it. It's kind of cool. So you're not gaining, it's zero knowledge in the sense that you're not gaining any knowledge about the number of grains in the bucket, but you are gaining knowledge about what that person knows. Okay, now, that's kind of cool, but here's the upstart version. So, okay, first of all, before we go there, so if the Amazing makes even one mistake, he's finished. But if he gets it right every time, the odds that that he would be so lucky are really vanishingly small. And so we will believe him. Okay, now here's the upstart variant. Amazing, he comes to you and he says, I want to tell you how many grains there are. I've been frustrating you all these times, but I want to tell you. And Amazing tells you some number. Okay, now a bucket of sand has a lot of sand, okay, and that's a lot of grains. It's like maybe millions. Okay, so he gives you some number in. Okay, how can you be sure? You really don't want to count them out. You really don't. You really don't. Yes?
You can take several buckets, separate that bucket of sand into two, and put random sand in other buckets and keep track of which two are the real ones. Then ask them to count every single bucket and add the two. And if it's the original number, then it's true.
I mean, but really then you're just testing for consistency. Because if you, suppose he says 10 million, nice round. So now you divide into two buckets, and you go 6 million and 4 million. Okay, that's consistent. I mean, you're right. If he said 6 million and 3,999,000, you know he's lying. But if he's consistent, but he could still be lying all the time. Don't you? Maybe I'm not understanding.
But how would he lie?
How would he lie? Well, because you're just dividing up the sand, right?
No, then you put in other buckets with random amounts of sand, and you won't know which two buckets come from the original bucket.
Okay, sorry. Say your whole protocol again.
So you have a bucket of sand,
Yeah.
and you divide it to like two, and you have
Using that same sand.
using that same sand. But then you take in more sand from outside,
Yeah.
and you add more buckets, and you put in random ones, so he does not know which two buckets come from the original ones. And then you just ask him to count them all. And then you would take the two buckets that are from the original one and you'd add them.
Oh, I see. So your idea being that then you'd be able to tell that at least he was consistent about which buckets that he chose. That is. So you have now 5 buckets. 2 of them have the original sand, and 3 of them have different sand. Yeah. Okay, but see, I'm assuming that Amazing really does know how to do grain assessments. But he wants to deceive you, just by maybe 5 grains. So he gives you some number. Now Amazing is good enough so that he can recognize how many grains there are in each bucket. Right? We're assuming that, because he's proved that to us. Okay, so now Amazing gives you a number that's a little bit off. But now he looks at your buckets and he goes, oh, well, you know, when I add up those grains, I know how many there are. Those two equal the original one. And I'm still going to give the number that's 5 off. Why did you do that? So you could never really know. But maybe something like that would be a good idea. Because this is an upstart puzzle. I don't know the answer. Okay, you know, I thought maybe you could do something like binary search and try to divide everything in half. But, you know, how do you divide it in half? How do you know that it's half? But you have to make this homogeneous assumption that he made before. I mean, it was an excellent suggestion, but how can you make that assumption? Grains aren't homogeneous. So, what you'd like to do is you'd like to do this in not linear work. Okay, linear means you'd have to count every grain. A work unit would be counting a grain, dividing a bucket into 2, or asking a question. Let's say those are your work units. Can you do this in, let's say, square root of n time? That would be okay. Log base 2 of n time. That would be even better. I don't know. And I don't think anybody knows. Very simple problem, though, at least to express. Okay, by the way, do we have until 5 or do we have, or just until 4:45? Okay. So here's what I want to do now. I want to, did anybody solve the campers problem while we were talking about other things? Okay, I propose to solve it, and then I propose to do a little mind reading exercise, a little mind reading game. Okay, that'll be our last thing. So the campers, you guys were very close, actually. So could our cameraman wake up? Can you wake up? Aim over here. Sorry. Okay. So here we have 4 paths. Okay, so you go down one path. And now you divide up the campers this way. Okay, so now let's look at what happens. Really, there are only a few cases that we have to worry about. First, one case is that all the groups agree, except, let's say all the groups agree. In other words, whatever their answers is, they all agree. Well, if a group agrees that it's a group of 3, they must be telling the truth. Okay, so if they all agree, then we trust the groups of 3, and we don't care actually what the group of 2 says. But of course, we know that we didn't find it. So if there's no disagreement in any group, then we just trust the groups of 3 and ourselves, and then we know what to do. Yeah? So that's a no disagreement case. Okay, so now help me with the next case. The next case is there's disagreement in only one group. Which group? Doesn't matter. Only one group. I mean, let's say, I assume it doesn't matter. It might seem that it matters, but it turns out it doesn't. Okay, if there's disagreement in only one group, what do we know about all the other groups? They have to be telling the truth. Right? Because if there's disagreement with one group, in one group, there's at least one liar there. So let's say one of the 3s has disagreement, these 2 must be telling the truth. So if there's disagreement with one group, in one group, we just forget about that group. We just trust everybody else. That's the second case. Now there's one more case, which is a disagreement in 2 groups. So this group, this is fine. And this is disagreement in 2 groups. So what do we do then? Yeah, go ahead.
Okay, so one of those groups must have 3. So you so if one of those groups of the disagreeing groups has 3 people, then the 2 people from the group that has 3 people in disagreement must be telling the truth.
Exactly. If there are 2 groups of disagreement, there can only be 1 liar in any group.
So
we take the majority of some 3 groups.
yes, and then you just take the answer of whichever group is in agreement.
Right, so if we have 1 3 group and 1 2 group that have disagreement, we take the majority here, we take this group because they're all agree, that's fine, and then we ignore this group. And then we know what to do. Okay, now I leave it as, and that's all the possibilities, right? Because there can't be disagreement in 3 groups because there are only 2 liars. Okay, now, suppose you only had 7 campers. Why is that not enough? All I'm going to say is that we're going to use something called the pigeonhole principle. Does anybody know what that is? Yes.
Okay, so if you have n holes and n plus 1 pigeons, then after, and let's say for some reason you want to put the pigeons in the holes. So let's say you put n pigeons in the holes, and
If some hole has to have at least 2 pigeons.
yes.
Exactly. Okay, same idea. If I have only 7 campers, then 2 paths cannot have more than 4 campers. There's some 2 paths that have 4 campers or fewer. Okay, because imagine that I have 7. Okay, again, I take 1 path because that's clearly the best thing to do. But now let's say I'd have 3 3 and 1, or 3 2 and 2, whatever. I'd have 2 paths that have only 4 campers. Okay, in which case, if I had 2 that lied and 2 that didn't, I wouldn't know which one to decide. It's a little bit informal, but you get the idea. Okay, I guess I won't be able to do magic. So I'm going to just show you one last thing. We have a website of games. It's called, you look up, just look up Dr. Echo. You'll see lots of games. And one of the games, and then I will let it go. It's going to show you how this goes. Bigger. This is actually a French version of the game. Because people did it in France, and so that's what happened. But anyway, the game goes like this. You're trying to get territory, and trying to get as much territory as possible. So the first player goes, and then the second player puts something there. And what happens is that all of the area that's white is going to belong to the second player because those are all points that are closer to the, well, we're calling them stones that the green player has put than to any red point, and then to any point that's closer to the red stone. This one. And now red goes again. So let's say red goes here. So it's the same idea. So these are all points that are closer to that red stone than to the green stone. So now if green goes here, let's say, it keeps going like that. Now it turns out this puzzle was inspired by a war that happened between Great Britain and Argentina over some islands that are way in the South Atlantic. And at the time, people were wondering why Great Britain would care, because all there were sheep on that island, on those islands. I mean, a few people, but mostly sheep. Well, it turned out, surprise, surprise, there's oil between those islands in Argentina. What a shocker. And people hardly ever have wars over oil. You never have heard of that. And so, it turns out that the law of the sea is exactly this. if you have an island and I have an island, and they're close enough together so we don't have, like, it's not open sea between us, then the oil between us is based on the perpendicular bisector between us. And so Britain wanted those islands so that it could get to the oil. What a shot. Okay, on that note, thank you very much. It's been a pleasure to work with you.